now that we have computed the first and second derivatives of the proposed particular solution, we are ready to substitute this into the differential equation and then determine the unknown coefficient. So we're going to turn to that. We go to this board here to see how that progresses. So we're going to make the substitution in the ODE that is given to us. And so here is the form for the second derivative that we had just obtained. So second derivative plus gamma times the first derivative plus the function itself equals f of tilde of tau. This is the forcing term in the equation. That's the equation we are solving. So we make that substitution, and then we can simply rearrange. We are going to rearrange them according to the coefficient. So if we collect all the terms that involve the coefficient a1, we have this grouping of terms. You can see that v1 double dot comes from here, and then we have v1 dot times gamma, and then we have v1 showing up here. But this combination in the curly brackets is actually equal to 0 because v1 is the solution to the homogeneous differential equation. So likewise, if we collect the terms associated with a2, we have a similar grouping now involving v2, but v2 is also a solution to the homogeneous differential equation. So this second curly bracket, those terms are also equal to 0. So what remains in this equation is this part here on the left hand side. So that is simply carried here, and then we have the right hand side shown over here. So this overall ODE collapses into this only surviving term on the left hand side equals to the right hand side. And so if we then say what is known and what is unknown in this equation, a1 dot is the only unknown in here. The Wronskian associated with v1 and v2 we know, v2 we know, and the forcing is known. So we move all of that to the other side of the equation, writing the equation as a1 dot equals minus v2 of tau times f tilde of tau divided by this Wronskian here. So this is now a first order differential equation for a1, and so we can simply integrate this equation. It's an equation with a1 dot equals some function of tau, which is known, and so we can simply integrate that, and symbolically that expression is written over here. a1 is the integral, minus sign taken outside, of this right hand side integrated over d tau. So that then determines the solution for a1, and the question then is how do we determine a2? And once we have determined a1 and a2 both, we are done with finding the particular solution. So we want to describe that next, and we begin by recalling that we had made a choice for a2 dot in terms of a1 dot. We had a boxed equation that we had looked at before, and that is exactly this equation. And now that we know a1 dot, we can substitute for a1 dot from up above, which gives us this expression here for a2 dot. And again, now a2 dot is entirely in terms of known functions of time, and so a2 dot equals this particular right hand side can also be immediately integrated. And so we can say, formally integrating that, we have a2 equals integral of this expression over d tau, and that gives us the new function a2. And so at this point we have found both unknown functions a1 and a2, and thereby we have completed the particular solution for this example that we were illustrating this with. And so I want to end this discussion by making some general remarks. This procedure that we have looked at is in fact more general, is completely general for second order linear differential equations. The particular example that we chose to show the steps for it would also go through for linear equations with arbitrary coefficients. It's a good algebraic exercise to verify that indeed it goes through. And actually what is even more interesting is that this method is also applicable to higher order linear differential equations. It only works for linear differential equations, but it applies to higher order equations also. So you can read about that if you're interested. And so this is a general method for constructing particular solutions for linear differential equations, and homogeneous solutions along with particular solution then provide the complete solution. And so next we will turn to a specific example where we'll work out the functions involved for a particular given problem.